right, let's talk about the very heart of the Windows operating system. Deep down, there's a single piece of code that holds all the power, and I mean all of it. It's the kernel. You can think of it as the ultimate authority, the central command for literally everything your computer does. But having all that power concentrated in one place, well, it creates a pretty tempting target, and that's a huge risk for all of us. So let me ask you this. What happens when that ultimate authority, that core you rely on, gets compromised? If an attacker can wiggle their way inside the kernel, they control everything. And I mean everything. Every password, every file, every single secret on your system is suddenly theirs. It is, without a doubt, the absolute nightmare scenario in cybersecurity. So this kernel, right? It's not some abstract concept. It's actually a file on your computer, a file called entosKernel.exe. And it operates with the highest privilege level possible on the CPU. It really needs this power to manage the whole system, but that incredible power paints a giant target on its back. For an attacker, getting control of the kernel isn't just one of the goals, it's the ultimate prize. And let's be crystal clear about what we mean by lost. We mean it is completely 100% game over. A compromised kernel can lie to all of your security software. It can tell your antivirus, hey, everything's fine over here, while it's shipping your data out the back door. It's the digital version of an intruder having the master key to every single room in the fortress. So, the big question is, how do you protect the most powerful part of the system? For years, the honest answer was, you really couldn't, not with absolute certainty. The solution required a totally radical change in thinking. It was a real light bulb moment. What if you could create something even more powerful than the kernel to stand guard over it? And this is where the whole architecture gets flipped right on its head. Traditionally, the kernel sat directly on top of the hardware. But this new model introduces something called a hypervisor. It uses special features that are built right into modern CPUs, things like Intel's VTX and AMD's SVM, to create a brand new foundational layer underneath the operating system. This lets it watch over the kernel from a position of even higher privilege, so high, in fact, that security pros sometimes call it ring -1. This whole new architecture has a name: Virtualization-Based Security, or VBS for short. The most important thing to understand about VBS is that it uses the power of that hypervisor to carve out these secure, totally isolated pockets of memory. These areas are completely invisible and totally inaccessible to the main operating system, creating a kind of digital safe that even a compromised kernel can't crack open. So how does this actually work? Well, VBS splits the system into two distinct worlds, which are called virtual trust levels, or VTLs. You've got VTL 0, which is the normal world. That's where Windows runs, where your apps live, just business as usual. And then you have VTL 1. That's the secure world, a tiny, highly privileged, and locked-down environment that's completely controlled by the hypervisor. Think of VTL 0 as a big, bustling city, and VTL 1 is the impenetrable watchtower looking down on all of it. Okay, so now we have this amazing new architecture, this secure watchtower. What's the very first thing we should use it to protect? Well, obviously, the keys to the kingdom, your user credentials. See, in Windows, there's a really critical process called the Local Security Authority, or LSA. You've probably seen it running in your task manager as lsas.exe. This process is responsible for managing user logins, passwords, and access tokens. And because it holds all that juicy information, it has always been the #1 target for attackers trying to steal credentials. And this is the exact problem Credential Guard was built to solve. It's a brilliant idea. It takes the most sensitive parts of the LSA and just moves them into that secure VTL1 world. It's like taking the crown jewels and putting them inside a vault that the rest of the operating system can't even see, much less break into. So here's how it plays out. When you go to log on, the normal LSA in VTL 0 gets the request. But instead of handling your secrets itself, it makes a special secure call over to a tiny, isolated process running in VTL 1 called LSA ISO-X. That little process is the only thing that ever gets to touch your sensitive password hashes and keys. So even if an attacker completely takes over the main operating system in VTL 0, they just can't get to the credentials. The watchtower in VTL 1 simply says, nope, access denied. Okay, so we've locked down the credentials, the crown jewels are safe. That's fantastic. But what about protecting the kernel from getting compromised in the first place? Well, VBS gives us a powerful tool for that too, by acting as the ultimate gatekeeper. In the world of enterprise security, control is everything. big organizations need to enforce really strict policies about what code is allowed to run with kernel privileges. That's because one of the oldest tricks in the book for attackers is to sneak in a malicious driver. That's why you hear so much about things like WHQL signatures. It's basically a stamp of approval from Microsoft that says, we've checked this driver, it's legit, and you can trust it. This is precisely what Device Guard is for, though you'll probably hear it called by its more technical name these days. Hypervisor Enforced Code Integrity, or HVCI, and it does exactly what the name implies. It uses our hypervisor, that guardian in VTL1, to act as the ultimate bouncer at the kernel's door, checking the ID of every single piece of code that tries to run to make sure it's properly signed and trusted. So what does this actually buy you? Well, first, it flat out blocks any unsigned or improperly signed drivers from ever loading, period. It can also enforce code signing policies on regular applications too, but maybe the coolest part is this. Even if an attacker does find a vulnerability in the kernel, the hypervisor prevents them from making memory both writable and executable. This single rule shuts down a massive class of common exploits, all because the hypervisor in VTL1 is enforcing the rules from a place the VTL0 kernel simply can't argue with. So when you put all of these pieces together, it becomes incredibly clear that this isn't just another security program you install. This is a complete and total redesign of the system security foundation. The most crucial takeaway here is the shift away from relying on a single, all-powerful kernel that could become a single point of failure. Instead, VBS creates a defense in depth, leveraging the hardware itself to build this small, highly trusted foundation that can enforce security on the rest of the much larger, more complex system. So let's just quickly recap the main points. At the very bottom, you have VBS, which uses the hypervisor to create that trusted, isolated VTL1 environment. Building on that foundation, you have Credential Guard, which acts like a vault for your most important secrets. And then you have Device Guard, or HVCI, which serves as that incorruptible gatekeeper for the kernel itself. Foundation, vault, and gatekeeper. This huge architectural shift really makes you wonder, doesn't it? As operating systems keep building these more powerful, hardware-assisted fortresses, is it possible the next generation of attacks won't be aimed at the kernel at all, but at the hypervisor itself? It really seems like the entire battle for control of our computers is moving to an even deeper, more fundamental level of the system.
If you want to help me out, please smash that like button, leave a random comment, and subscribe if you want to become a better hacker.